We continue review calculus 2. Determine if the series converges absolutely, converges or diverges. To be more specific, we say converges absolutely, the other one is converges conditionally. Or diverges. So the roadmap of this is, I'm going to write out here. So first, we will test for absolute convergence. That means we're going to put the absolute values into the term of the sequence and test for absolute convergence. So we test with the series with the absolute values. If it is yes, then obviously it is absolute convergent and we're going to stop. If it's no, we'll remove the absolute values and then test for conditionally convergent. So first we test the series where we put the absolute values in it, and now we test the series when we don't have absolute values, which is the original one. If it is yes, then it's obviously conditional convergent, and then of course we stop there. If it's no, that means the series divergent. The series is divergent. Right, so that's the roadmap. First, for the sequence like this, put the absolute values in, see what happened. First, we put the absolute values in it and see if it is convergent or not. If it is, it will be absolute convergent. Right, what the absolute values does is that any negative will turn to positive. So with the absolute values, this would be just a to the n. The bottom is positive, so absolute values or not doesn't really matter. So once again, the absolute values will kill on the negative and turn to positive. So we end up with just a to the n power. The bottom is 8n squared plus 5 to the n. Right, so now we have this. I will test for convergence or divergence of this one. Usually when there are more than one term like this, we do the limit comparison test so that we can just take the one that go to infinity the fastest. So compare these two terms, the 5 to the n, that exponential go faster to infinity than the 8n squared. So that's what we're going to compare to. But for now, let this be the sequence or the series a sub n. Right. Now what we'll compare to is the series b sub n where we'll take the highest term, the term that go to infinity the fastest. Now both of them in the power of n, so we move that. Now this is a geometric series. Well, it's right there. When the ratio is equal to a over 5, and this is outside of negative 1 and 1, so this series b sub n, the series of b sub n diverges. So this is a geometric series. Geometric series, and r is equal to a over 5, so it is divergent. So b sub n is divergent. Now, next limit comparison test, we're going to take the ratio of a sub n and b sub n. If it is equal to constant, then behavior of the series a sub n and the series b sub n will be the same. So that means since b sub n is divergent, a sub n is also divergent if that ratio is equal to a constant. Now that's what we're going to do. Right, so a sub n over b sub n, a sub n that is a sub n, and b sub n is this. So we just divide them. We kind of run out of space here, so I'm just going to say that divided by that, or that multiplied by reciprocal of this one. It should have more space on this problem. Multiply reciprocal of this. Now, we did have that 8n squared slower to infinity than 5 to the n, so we can just cross that out. We take the one with the highest go to infinity the fastest. Now, when we ignore that, I should not cancel like that. We just say the limit of that is the same thing as the limit of this. So the limit of this is the same as the limit of that. The 8n squared too slow to infinity. Now cancel everything. 5 to the n and 8 to the n. This is 1, which is constant or finite. So that means a sub n and b sub n have the same behavior. Since b sub n is divergent, we see that a sub n I'll just say it, the series with an absolute value is divergent. So with an absolute value, it is divergent. Now go to, so we test for absolute values, it doesn't work. Now test for conditional convergence. The test with absolute values doesn't work. Now remove the absolute values, just test the original one. I'm just going to test this. Yeah, I should have a lot more space for this problem. Right. Now, obviously we have the negative raised to the power, so I want to write that out separately. So that is called the alternating factor. And then we just have a to the n on the top, and 8n squared plus 5 to the n. Right. Now, so I can say negative a to the n. I can say negative 1 times 8, both of them to the n power. So both of them will go to the power of n. So that's what we have here. Take out the negative 1 to the n, and we write this as an alternating series where we have a sub n is this. Right, and we will test two things. First is a sub n is non-increasing or not. And second, does the limit of a sub n as n goes to infinity equal to 0? Right? So actually the second one is easier to check, so I'm going to check the limit of a sub n as n go to infinity. Right, so the limit here sorry, I really should have a lot more space, but look like the next one, yeah, the next one will not take a lot of space, so it's good then. Right, so once again 5 to the n go faster to infinity than 8 n square, so we just say it. And we put both of them under power of n. 8 divided by 5 is 1.6. 1.6 raised to some power. So that number just keep getting bigger and bigger. So this will go to infinity. So that means this fails. And so we say the series diverges. Right, let's look at the roadmap again. Absolute convergent is not. Conditional convergent is not. So it's going to be divergent. Right, next. We have that one. Oh, timestamp, sorry. Next we have this one. So first I'm going to throw in an absolute values into it. So now throw in the absolute values. And absolute values we turn all the negative to positive, and so we really don't have this negative sign. But before that, let's just do this quickly. Negative power, just move that to the bottom. Right, now the absolute value will eliminate all the negative sign. All of them will be positive. Right, now is this series convergent or divergent? By what test? Well, if we write this as to the n power, and it's just like the last one, this is a geometric series, but unlike the last one, r is equal to 1 over 3. And since r is between -1 and 1, this series is convergent. So what we have here is with the absolute value, it is convergent. So we say the series is convergent absolutely. And just like the roadmap, with an absolute value, it is convergent absolutely. So we stop. Do not go any further. If it doesn't work, go to conditional convergent. That is without the absolute values. And then we test again. So that was that one. Right, now we have this one. Ouch. So we might not be able to do this. That look complicated. Okay, first let's just see what happened. I'm going to put the absolute values in it. Right, the absolute value will eliminate the alternating factor. By the way, let's look at this. 6n plus 5 over 6n plus 4. So that is a little bit bigger than 1, right? And ln of something bigger than 1. Just look at the graph of the ln of x. We might see this a lot for this problem. Ln of 1 is equal to 0. So if we have a number bigger than 1, the graph is over here, so it's going to be positive. So that's why absolute value or not, it doesn't matter. Absolute value is positive, it's itself. It only eliminates the alternating factor, because 6n plus 5 over 6n plus 4 is going to be bigger than 1, therefore ln is going to be positive. Right, what can we do here? It's ln, so that's for the reason that we can split them. So we split them. Have ln of 6n plus 5 minus ln of 6n plus 4 right, and then what? So it's ln and like that. So pretty much I looked through this table. I'm not sure what to do here. One thing we usually see when we have a positive and negative, that is telescoping series. So let's see if it works. Let n equal to 1. So put 1 in here. We have ln of 6 plus 5, 11, minus 6 times 1 plus 4, so ln of 10. That works. 1 positive, 1 negative. Sounds good. Next, put 2 in for n. Oh, shoot. 2, that's 12, 5, that's 17. Minus 6 times 2 plus 4, that's 16. And now next, n equal to 3, 18, and 5, 23, minus ln of 22. Bad news is this is not telescoping series, even though 1 positive, 1 negative, nothing cancel here. So that doesn't work. The telescoping series doesn't work. So like I said, when look at all the tests, yet none of them are obvious. Sorry. None of them are obvious. The only thing that I can think of course, the direct comparison test or comparison test, they might be a series that we can compare to, which like I said, it's not obvious. I don't see it right away. What I can see it is, well, we did say that it is positive, right? Also, that is continuous. And is that decreasing? You know where we're going with this, right? That is the integral test. Because that look like ln, if we integrate this, it's not that bad if we have to integrate it. But we just need to check this. It's positive. Well, we already check it is positive. And it is continuous, because as long as this is bigger than 1, it is defined, so it's continuous. Now it's not decreasing. Right, so I'm just take the derivative of this. I'll take the derivative of ln. I'll use x instead. We can take the derivative of this, but this is easier to do. It's going to be 1 over 6x plus 5 6x plus 4, and then times derivative of inside, which is a quotient rule, u prime v minus u times v prime over v square. Now notice that this is positive when x bigger than 1, greater than or equal to 1, it is positive. And here on the top, it's simplified to just 36x plus 24 minus 36x minus 30. Right, so indeed it is negative. Now if it is negative, that means the function is decreasing. So that means we can use the integral test. Now for integral test, just go ahead and integrate. It's not that bad. But like I said, that's the only thing I can think of now. Because of that, integral of Ln, integration by parts. After that, we determine if it is positive, if it is convergent or divergent. If it is divergent, then we have to do that without the absolute values, which also is more problem. So actually, I'm just going to omit this problem from the review. If you want the answer, just let me know. I will send that to you later. But let's focus on the review. Let's not focus on this problem. That would take too much time. Right. But the integral test, yeah, it checks all the boxes. Should be able to integrate this. Right. Right, next, determine the divergent and convergent. So here we have a few series, and did not tell what test should we use. Right, so what test should we use? Usually when we look at this, especially these two, where the top or the bottom, where we have fraction, where the top and bottom have more than one term, it will be easier if we use the limit comparison test and just compare the term that go fastest to infinity. So for that, if I write this series as the series of a sub n, I would choose the series where I use only the highest, the term that go fastest to infinity. So we say b sub n. I'm just take the one with the highest power. In this case, also the fastest term to infinity. Right. Now let's split the square root. Right, so that's what we have. Now, that gives us n to the 3 halves, right? By default, this is to the first power. So if we cancel out the n, one n from the top, one n at the bottom, what we have is 6 over square root of n, square root of 5, n to the 1 half. Now, the 6 over square root of 5 doesn't really do anything to the sequence, or do to the series. What is important is this term, and that is p series when p is equal to 1 half. So b sub n diverges. Now we have two series. Now if we take the ratio, if the ratio is constant, that means they behave the same. And because of that, it is going to be divergent, because b sub n already diverge. A sub n is going to be this mess. And divide by b sub n, which is this, or this, or that, doesn't matter, b sub n. But I'm going to do that in the reciprocal. So I'm going to flip. 6n will go to the bottom. The top, actually, we can use any one of them. Sorry, just 6. The bottom is square root of n, square root of 5, sorry, n to the 1/2. Right, next, because we have 5n cubed, go fastest to infinity compared to 4n, and 1 doesn't go anywhere. So we just ignore those. The limit is equal to. So that's why the limit comparison test is very common, because that simplifies the problem into something a lot easier to work with. So just take the 6n on the top, because 6n goes to infinity, the 4 doesn't go anywhere. Right. Again, go to 6. Square root of 5. On the top, there's square root of 5. And here to the first. And n to the 1/2. 1 and 1/2, that's 3/2. At the bottom, we have square root of 5. I will split it. Of course, that also n to the 3/2. That's the same thing as we did before. That is n to the 3/2, so that cancel out. That cancel out. And this is just equal to 1, which is a constant or a finite or constant. So for the limit comparison test, if we have the limit of the ratio equal to a constant, where was that? Right here. If it is less than infinity, meaning it is finite, and b sub n is diverges, so the behavior will be the same. So that diverges, b sub n diverges, the ratio is finite, meaning that behavior will be the same. So since b sub n diverges, a sub n diverges as well. Right, so that's what we have. Right, next, of course, we also use the limit comparison test, because they're more than one term. It's nicer to just drop one of them. So first we write this as a sub n. Sorry, first we just say that it is a sub n. Now, b sub n. B sub n is where we drop the term that slower to infinity. We take the fastest term to infinity only. One for the top, one for the bottom. Alright. Now we can split this, the 5/4 power go to 2 and go to n. N to the 5/4. Right, let's just rewrite that a little bit. 4 and 2 to the 5/4, that is constant. And then we have 1 over n to 5 over 4. So what's that? Well, this is constant, and we have n raised to the index raised to that 5 over 4. Well, that is a p series. P is equal to 5 over 4 bigger than 1, so diverges. Right, now we know b sub n is divergent. If we take the ratio of a sub n over b sub n, and that is a constant, then they behave the same. Right, a sub n is that divided by b sub n. You can either use this or that, doesn't matter. I'm going to just use this one. Yeah, this is the b series. Even though there's a constant here, remember the constant, we can always take it outside of the series, so that does not change the convergent or divergent. If the series is convergent multiplied by a constant, it's still convergent. Same thing for divergent, multiplied by a constant, is still divergent. Right, so yeah, so I'm going to take use this as b sub n, and since we divide by b sub n, it's multiply the reciprocal. The 4 goes to the bottom, 2 to 5 to the 4 on the top, and then n to 5 over 4. The 4 and the 4 cancel out. That constant doesn't do anything. Both the n and the 2n plus 4 of that. Yeah, we can even bring that. Actually, both of them have the power of 5 over 4, so why don't we just keep that 2n like this? It's much more convenient that way. So now all of them have the power of 5/4. So we have 2n, and then 2n plus 4. Now, sorry, at n goes to infinity, this goes to 1, right? 2n faster to infinity than 4, so just ignore the 4. 2n over 2n is just 1. And 1 to the 5/4 is equal to 1, which is finite, or constant, a finite constant. So that means behavior of b sub n and a sub n will be the same, since b sub n is divergent. Wait a minute, this is a p series when p is bigger than 1, that is convergent, sorry. And it's greater than 1. Right, So it's finite, behave the same, and B sub n convergent, so A sub n is convergent as well. Here the P series, P is 5 over 4. Yeah, this series, the constant multiplied to a convergent series is still convergent. So B sub n is convergent, they behave the same, so A sub n is convergent as well. Right, now we have this. We have the negative exponent. Let's move that to the bottom. Right, so look like we have a mixture of an exponential term, this one, and the power n to the fourth, that. So usually when we have the mixture of two things like that, we use the ratio test. If there's more than one term, we have to go to limit comparison test, ignore every term that goes lower to infinity. So the limit comparison test usually the go-to test, where we just want to ignore a few more terms to keep things, to simplify things. Now this is already simplified. The only thing we can use is the ratio test. So A sub n is equal to n to the fourth, e to the 2n, and then we just take the ratio test. A sub n plus 1, the next term, divided by this term. Right. Now we have enough space. So n plus 1, substitute in here. N plus 1 substitute into n. Divided by A sub n. So n plus 1 to the fourth power. Do we really need the absolute values here? The answer is no. All of them being positive. Absolute values is redundant. Right, e to the 2n plus 2. Multiply this out. Now, divide fraction is multiply reciprocal. N plus 1 to the fourth power. At the bottom we can split e to the 2n, e to the second, right? Exponent, properties of exponent. Cancel that. Right, e squared is a constant. Both of this under the power 4, so move that into the power 4. And e squared, we have that at the bottom. Now, as n go to infinity, n plus 1 over n go to 1, right? Once again, n go too fast to infinity, n goes to infinity, the 1 doesn't. So we keep the n over n is 1. So this is 1, and we just have 1 over e squared. E squared is bigger than 1 for sure, so this is less than 1. So what it says about the ratio test? The ratio test is less than 1, it is convergent. And that's pretty much it. So when we have of a few terms, different terms in the row rate, this that's usually a ratio test. When we have a ratio, a fraction of more than one term, it will be useful if we do the limit comparison test to ignore the term that doesn't go to infinity as fast. Right. With that, I stop the review here. As always, thank you for watching. See you in another video in review for Calculus 2.